Today we'll be making real USB requests to the device. We'll make requests similar to the ones that host sends to get descriptors. We've seen those before. The ones that have request type, value, index, and length. Except in this case we'll set all these values ourselves and we can program the device how to react to those custom requests. Sending a custom request is relatively simple. The kernel API provides functions to do that, listed here on the slide. The one that we're interested in, the USB control MSG, would take information to send in form of those 5 fields, as well as some information about the device. This function will then construct something called USB request block, or URB for short, and send it away. Now, you may ask how to get this information about the device this function needs. Well, there are 2 pieces of information. The first one is created by the kernel itself when the device is attached. It is passed into the probe function. We only have to write it down and later retrieve. The second piece describes what endpoint and what type of transfer should be used, as well as whether the data is going to go into the host or out from the host. The kernel API has functions to construct those, so it wouldn't be a problem. The second piece is called a pipe. Let's take a closer look at it. It's a 32-bit integer that contains information about where the data will flow and what type of transfer should be used. You may ask how one would fit several pieces of information into a single integer. Well, I could split this 32-bit integer into several smaller integers, then combine them. The thing is, when a pipe is constructed, parts of information are written into different parts of the integer. This integer then becomes something called a bit field. This is actually done by a separate function. We should not worry too much about it. While sending a control message, one of the fields we'll have to fill is called a request. We've been dealing with it before while programming the device. It is the one that describes an action to perform. It may be a get descriptor or set address or set configuration. In a custom request, this field could be any number as long as it's not a standard one like set address. The list of standard requests is presented here on this slide. While recording though, I decided to use standard get status for in transfers and the set feature for out transfers. Another field we'll have to consider is called request type. It contains information about whether the request is standard or not, whether it is addressed to a device as whole, to interface or endpoint, and importantly, whether it is an in or out transaction. Now I'd like to make a few technical remarks. First is, there will be 2 different structures describing the device, called USB device and USB interface. The difference is, an interface is kind of a logical device, so a device, a physical device, might contain several interfaces. We agreed to only use one interface in the device for simplicity, so this structure describes same thing from different angle. A driver is attached to an interface, not a device, thus the driver will have access to the interface structure. The functions that send requests, though, take a USB device as a parameter, so we'll have to convert one into another. Luckily, the kernel API provides a function for that called interface to USB dev. We'll be using it in the code. Second, there is a type of warning that appears in the kernel log only once. These warnings may contain important information for debugging, but if you've missed them, they won't appear again. This function can be reset by executing this command here on the slide. So, if some function is just not working without logging any error, it makes sense to try running this command to reset this warn once thing. And last, we'll have to create buffer in a heap. In regular C code, it is done with the memory allocation function, the malloc. Well, the kernel has its own function for that. It is called kmalloc and takes one additional parameter, the flags, that describes where the memory should be allocated. In the simplest case, we get to decide whether it's going to be allocated in kernel space or user space memory. These flags have GFP prefix, which stands for get free pages. So, to allocate a memory in kernel space, the flag has to be GFP kernel. That's it for the theory part. We're good to go to the IDE. We're going to be sending control messages, and I remember that functions that sends them has a control MSG in its name. So I'm searching for this function. It's definitely located in the USB.h header, and here it is. We have a bunch of other functions in this file like control message receive and send, which are wrappers for this function. There are also functions to send interrupt and bulk messages, but we'll only focus on this one, USB control MSG. Let's see what it needs to do its job. It takes something called USB device, a pipe, a bunch of values we've seen before, like request type, request, value, index. These are contents of the setup packet and are going to be sent straight to the device. These values are followed by a data pointer, size, and timeout, so we can send some data after the setup packet. Remember not to exceed 64 bytes, its maximum packet size. Let's focus on the first parameter, the device structure. Well, we have to get this one from somewhere, but first I create a variable for it. Luckily, we can get the device from the USB interface structure, which we have here in the probe function. So kernel creates this structure when the device is connected and passes it to the callback. Finally, here is our USB device. Back to the header, next we need to define a pipe, a bit field that defines the source and destination of the data as well as transmission type. Transmission type will be control, so I'm looking for a control pipe. Here are two defines for send control pipe and receive control pipe, as well as for some other pipe like isochronous, bulk, and interrupt. I'm gonna take this one because I'm sending control request to a device. I'll place it here in the write function, so the number that the user writes to the file will be sent right to the device. Its type is unsigned int, the device is the one we retrieved a moment ago, and the endpoint is 0, the only one we have for now. Now we need to define all the variables that are going to go into actual request. I'm copying them from the header. Endpoint will be 0, request will be set feature, although it's not important now. Request type will become important a bit later. For now I just leave it 40 hex. Value will be the value we retrieved from the user converted to number. Index and data I will not use here, so they will stay 0. Now I need to call the function itself, and here I realize that I've been filling the arguments for other function. The arguments are similar though, so it shouldn't be too big of a problem. I paste the function here, fill in the device, the pipe you've created, and other parameters. Leaving timeout as 5000 for 5 seconds. I think we're good, let's try to build this. Of course, there are errors, a lot of them. I'll start at the top. This one tells that the variables should be declared separately before any functions are executed, so I'm moving these declarations on top. I just realized I can reuse this endpoint variable. I'll build the module again, but first clear all this mess in the terminal. The new first error is about variable name. I have this value declared twice. I will rename this kernel side buffer to value str. Build again. This time it says this pointer should not be const. I'm fixing it. Repeat again. Now it says that my value variable is not used, but I'm sure I've listed it among parameters to the USB control MSG function. So I'm copying again the list of parameters from the header file. Substituting them again with my real variables, I forgot to remove this asterisk symbol, fixing it. Build again, and this time there are no errors. Inserting the module and looking at the log. This time I have high hopes to send actual USB request, and I want to see it, so I'm starting Wireshark in a separate terminal window. I need to reconnect the device so that its USB address shows up in the log. The new address seems to be 8. I'm inserting this new address in the Wireshark filter, double checking that this module has executed for this device, and writing some numbers, say 34, into the device file. I do see the new request in the Wireshark. Request number is 3, which is right. Value is 0, which is not right. It should be 34 because I have written 34 in the file. The kernel log says it did receive the right number, so there is a bug in the code. Right here, I am setting the value before I've converted it from the user string. Actually, I don't really need this variable. I can use the value underscore L here. Building and reinserting the module again after the fixes, writing to the device file again and checking Wireshark. This time I have written number 65 and I see 41 hex here in the request. 41 hex is 65 decimals, so it's okay. The response contains no entity error because it's not implemented in the device side. Let's now add the same functionality to the read function. I'll copy this whole piece of code as we'll need only minor changes in it. I won't need this buffer anymore, but I'll need those variables and this USB control MSG function. Now this send pipe needs to be transformed to receive pipe since we're reading data from the device. This set feature has to become something more appropriate to get request, for example get status, although it would probably work as it is. I won't need this data pointer anymore and its size, but I still need the value variable. I also need a buffer to write the device's response into. I'll use this array, just rename it to value underscore str. This module will output its contents, so it needs to be copied to the user space buffer. Its contents will be reported to the log and its length is returned for the first time read. This value underscore L does not exist anymore, and this data pointer has to be substituted with the value str because that's where we want the device response to be written to. This size becomes size of the buffer. That looks good. I built and reinsert the module. The log looks okay, trying to read the device file. Opening Wireshark, I see a bunch of new transfers, but those are out transfers, which is weird because we want to read data, not write. Checking the log to see maybe something went wrong. It looks like something definitely gone wrong. Here at the top I can see the description saying bug with controlled year and something more. I guess I'll have to search what this message means. I enter this text in the search prompt, removing filter, and there is only one result. That's a good start. And what we have here. First, this is a warn once thing that I was talking about in the theory section. This message won't appear in the log again unless you reset it. Here I run the read again and no new messages appear. That one is from the previous time. Second, the nature of the error. The direction of the transfer is set in two places. The direction of pipe, we have changed it to receive pipe, and the request type. Its most significant bit specifies the direction. Well, for our case, the request type is still out. This is the cause of the error. That's no problem, I only have to change the most significant bit here. Now I'm doing whole rebuild routine again. Reading the device file, checking Wireshark. This time there are the in transactions, but the response status is E again. That's not good, the error should be no entity. Checking the kernel log, there might still be an error. There is an error, and here at the top it says the transfer buffer is on stack. I'm searching for this error in the code. Again, there is only one single match, and again it's the warn once thing. It looks like all it does is checks if the transfer buffer is located in stack or heap. Well, my buffer is allocated in a local variable inside a function, and it will stop existing when the function returns, so it's reasonable not to accept this buffer. To fix it, I'll create a buffer in a heap. So I'm creating a variable that will be pointed to this buffer. And do actual memory allocation here in the initialization function. There will be 8 bytes in kernel space, thus gfp_kernel. I also have to deallocate this memory here in the exit function. Now I pass this buffer here in the control message request function, and now it should work. The value str is no more needed, and the size becomes more hard-coded 8 bytes. Replacing all the remaining instances of the value str, and we're ready to build this. Okay, I need to include the header for memory operations. They are defined in the slab.h. Rebuild the module again. Try reading the file. Open Wireshark, and here is the request with no entity error. It will be gone as soon as we implement the request in the device. Checking the log to verify there were no errors, and looks like we're good. So what's left is to implement this request on the device side, which we'll do next time.